Hi, welcome once more. It's Physical Sciences, and let's learn together. Let me take you through this lesson for today. And as you know, we are doing Physical Sciences Grade 12. My name is Tinyiko Kosa, and today we will be looking at a section under the knowledge area called Waves, Sound and Light, and we'll be talking about Doppler effect. Now, let's quickly look at what Doppler effect is all about. Now, here in this lesson, we will try and define what Doppler effect is. We will also try and look at how can we predict changes in observed frequencies. So we will be predicting what is going to happen with the frequencies that observers or people or detectors are going to observe as the source and the observer move in relation to each other. Now, they move in relation to each other. Now, you would realize that for grade 12 physical sciences, when we look at Doppler, we look at the two objects and we make sure that when we look at one moving, the other one should be stationary. So we don't look at both at a condition or at a situation where both of them could be moving. So every time we look at one object moving, the other will be stationary. In other words, not moving. It will be at rest. We are also going to make use of the Doppler effect equation to solve problems. And right at the end of the lesson, we will be talking about application of Doppler effect. Now here it will be just a discussion on how Doppler effect is applied on our everyday life and how does it help us in certain things in our lives. Thank you. Now let's move on and let's start to unpack this. What is Doppler effect? Now we are going to define Doppler effect generally now, not restricting it to sound, which is mainly what happens. We'll say that Doppler effect is the perceived change in the frequency of a wave, the frequency of a wave emitted by a source, emitted by a source due to the relative motion of the source and the observer. Now, when we define it in this way, we make it applicable to any wave phenomenon, be it sound, be it magnetic waves, be it any other type of waves, water waves. We can be able to apply it in that way. But when we come to sound, if we are going to be specific to sound, of course we can put something that has to do with sound in that particular definition. But then let's come back to this. When do we experience Doppler effect? When is it observed? We observe it when we look at water waves. We observe it when we look at sound waves. We also observe it when we look at light waves or electromagnetic waves. Now, it means that the frequencies of these wave types of waves can be changing, can be perceived to be changing when something happens to the medium in which the waves are moving. In this one here, the waves will be moving in water. So water becomes the medium. Here, the sound, we know sound in this case will be talking about sound moving in air, but we know that sound can also move in water, right? and in some other solid substances. So whatever it moves in becomes the medium. Now, light or electromagnetic waves. Here, we know that light actually moves even in a vacuum, space without air. But then, we're not going to dwell much in this one in particular, but our Doppler effect section will concentrate a lot on the sound section of our waves. Now, let's look at what happens when sources move or observers move in relation to each other, a source and an observer moving in relation to each other. Let's check what happens. Here is an illustration. We are going to look at change in frequency as observers and sources move in relation to each other. Now, let's look at water waves in particular. High frequency wavefronts are closer. High frequency wavefronts are closer together when a source is moving to a particular direction. Now, if you look at this illustration here, or this picture here, you will see that that point there represents a source. So I'll put an S for it. Now, this source is moving in that direction as indicated. Now, as it moves in that direction, you will see that there are wave fronts here, and I'll put dots where the wave fronts are. Okay? You will see that these wave fronts here, compared to the wave fronts behind the source, the wave fronts this side are bunching up. They are becoming or getting closer and closer to each other as the source moves to the right. And this side here, we see that the wave fronts are actually moving further and further away from each other. Now, this section here will indicate an increase in the frequency. So this section here indicates increase in frequency, in the frequency of the waves. Now, this would mean that whoever is standing at whatever point watching this happening will think or will observe a change in frequency between the frequency of the source. Remember, there is the frequency of the source and the frequency of the waves as the source approaches the observer. So that person or detector will record an increase in frequency of the waves. At the same time, if we have an observer this side of our picture, because these wave fronts here are actually moving further and further apart from each other, this section here indicates a decrease in frequency. So we have got a decrease in frequency here. And what I'm talking about here is what the detectors are going to register or the observers are going to perceive. So they will perceive a decrease in frequency here. But we don't need to lose the sight or the fact that this source, the frequency of this source, let me call it Fs, is not changing. But what we observe and what we see seem to give us a change in the frequency of that source. So that is basically what is happening here, and that is basically the issue around Doppler effect. The change, the apparent change in frequency compared to the frequency of the source as the source and the observer move in relation to each other. From the water waves, let's now look at the sound waves and see how Doppler effect manifests itself within the sound waves. How do we observe the Doppler effect there? Now, with sound, we know that high frequency sound is related to high pitch of that sound, right? So if you hear the pitch sort of the sound sort of increasing, and it's getting more and more audible, the sound, and you're hearing it more vividly than before, it means something, whatever is creating that sound is approaching you. So frequency is related to the pitch, and if we have got high frequency of that sound, we would have a high pitch. In the same way, low frequency of sound will relate to a low pitch for that particular sound. And this is when something is moving away from you and that sound is fading and fading until you just can't hear it anymore. Now let's quickly look at this diagram here, illustrating Doppler effect on sound waves. Now here is a source, S, right? The source is moving to the left as indicated by that arrow. Now 1 and 2 are representing observers or detectors. So these are observers. 1 and 2 are observers. This observer here at position 1, the source is approaching that particular observer. As we can see there, that the wave fronts for this sound, it's actually, the wave fronts are actually bunching up. They are more and more closer to each other. And like I have explained earlier with the water waves, that bunching up of the wave fronts tells us about an increase, an apparent increase in the frequency, the observed frequency. Let me represent the observed frequency as FL. So for this side, it means that the observed frequency is getting bigger than the frequency of the source, or the actual frequency of these waves. So that is what is happening on the left side, or that is how the observer number 1 here is observing the frequency. But when we look at the right-hand side of our source, you would see that these wave fronts are actually moving further and further away from each other. Now, these represents a decrease in frequency, like I shown earlier on with the water waves. Now, this would mean that the frequency as observed by the observer or listener is actually getting less than the actual frequency of the source. So that is very important for you to understand. We're looking at a source moving. We're looking at a source moving towards the observer, which is the section here of the source moving towards 1. We also have a situation where the source is moving away from the observer, which in this case is represented by the right-hand side of our source, where the observer is observer number 2 here. So we have got 2 situations there. In the same way, we can look at the light, although we're not going to spend much time on it. Check on how Doppler effect is experienced or occurs with light. Now, light, we know, can also be seen as a wave. And we'll talk about this more later on as well when we talk about the quantum theory or quantum mechanics, where we also look at light as a particle. So light has got this dual nature. We can explain it as a wave. We can also explain it as a particle. But more of that will be coming when we deal with that lesson on photoelectric effect and some other aspects that has to deal with the quantum theory. So looking at the wave nature of light, we know that a wave would have frequency. Now, high frequency of light is associated with colors like blue, like violet. Now you will remember from your electromagnetic spectrum that we have done already at grade 11 and grade 10, a bit of it, that you've got colors associated with frequencies from red to violet. So the section of violet, blue, indigo, that side, we're talking high frequency section of our electromagnetic spectrum. So when we have high frequency light, we will be associating it with the blue, violet colors. But we also have low frequency light. And the low frequency electromagnetic spectrum is associated with colors like red. Red is right at the end, at the far left, when we actually order these colors in terms of increasing frequency. You start with red down to violet. So if we talk low frequencies of light, we should be seeing more of the red color of that light. If we're talking high frequencies of light, we'll be talking the blue and the violet, and some of the colors that we may not be able to perceive with our own naked eyes, natural eyes. Right, so this is more or less how Doppler effect manifests itself in the different types of waves that we've looked at. Water waves, sound waves, and light waves. Now let's move on and begin to look at how do we calculate for frequency changes making use of the Doppler effect equation. Now, we're going to, like I said, keep this around sound mainly. So we'll be talking mainly about frequency changes around sound. Now, there is an equation that we're not going to derive for you and try to find out where it started and where it ended. Why did we come to the final equation of Doppler as is, as you know it? But we're just going to use it, which is what we are expected to do. Now, the Doppler equation says that the observed frequency, which I will call FL, is always given by the velocity of the waves in the medium plus minus the velocity of the observer divided by the velocity of the waves in that medium plus minus the velocity of the source. All this must be multiplied by the frequency of the source. Now, this is an interesting formula, if you like. Now, let's try and unpack it, and we'll try to relate it to what we have discussed already in terms of a source moving towards the observer and a source moving away from the observer. And we will also look at a situation where it is the observer moving towards the source or the observer moving away from the source. So we'll be looking at those situations and see how we use this equation or this formula to solve Doppler effect problems. Now let's unpack it. Like I said, FL, this is the frequency of the listener, the frequency as observed by the listener. And Fs is the frequency of the source. Fs, S for the source. And VL is the velocity of the listener. And sometimes we'll say the velocity of the observer. Now, so for that reason, maybe you might find sometimes books referring to that VL as VO, but we will keep it to VL. Vs is the velocity of the source. The source, we mean that particular object from which the waves are coming from. That particular object that is creating those type of waves. So, or generating them. We refer to that particular object as the source. Now let's look at the different situations where we have a source moving towards the listener and a listener moving towards the source. Now let's start with observer or listener moving towards the source and see how we're going to make use of our Doppler effect equation. Now when the observer is moving towards the source, we know firstly that the frequency of the observer is going to be greater than the frequency of the source. The second thing that we know is that the velocity of the source is 0. It is stationary, so the source is stationary, it's not moving. So what is going to happen here is that applying the Doppler effect equation in solving the problem when we want to know the frequency as observed by the listener, we would say that, okay, this will be V, which is that one there. But we are saying as the observer moves towards the source, the frequency that the observer is actually detecting is actually greater than the frequency of the source. Now, mathematically, this is a fraction. Now, if we want to make this fraction bigger because it's going to multiply the frequency of the source, we should have a bigger numerator and a smaller denominator. Now, that is the logic that we should be applying here when we solve most of these problems. If that frequency that is going to be observed is going to be bigger than the frequency of the source, we need to do something about that fraction that will make it bigger. And the only way to do that is to make sure that the numerator is bigger and the denominator is smaller. How do we do that? Let's come back to the equation or the formula. Now, for the numerator to be big, we therefore need to add. We cannot subtract when this denominator has to be big. We can only add to make it big. So it means it will be V, which is the velocity of the waves in the medium, plus the velocity of the listener. We can't say minus. If we say minus, then we'll be bringing it down, yet it should be getting bigger. That will be divided by the velocity of the waves in the medium. We want to make this one smaller, but we know that the velocity of the source is 0, so it's not going to make any difference, but we need to put it in there because what we are talking about here is scientific principles, it's science concepts that we need to clearly convey to whoever is going to be marking our work. Remember, you will be having your script sent to a particular point when you write at the end of the year, and those of you who are watching but just going to write in the February, March, you know somebody else is going to mark your work. You need to show that person that you understand what you're talking about. Hence, we have to even place it. Even if we know it's 0, we need to say this will be V minus 0. Why minus? Because we know that the denominator has to be smaller for us to have a bigger fraction that we are going to use to multiply the frequency of the source with. So there we go, and we say multiplied by the frequency of the source. Now, this also helps us because as we move further in our studies, we are not only going to look at the observer moving and the source stationary, and therefore the only thing that matters will be the velocity of the listener. No, sometimes at university level, you will be looking at situations where both the objects are moving. You should be able to do this without any problem. So this will be our way of writing down that formula here. If you like, this formula at this point is general. Okay? It's given to you like that in the formula sheet, in your question paper, then you must be able to use it. And the way to use it is this. When a listener is moving towards the source, that's how you're going to work this out and get your observed frequency. Now let's come to the next situation. The next situation is that we have observer moving away from the source. Now, when the observer is moving away from the source, what is happening with the observed frequency? Moving away from the source, the observed frequency becomes less than the actual frequency of the source. All right? Again, the velocity of the source is 0. The source is stationary. Now, let's quickly see how we're going to use this formula. FL, the frequency of the observer, or the observed frequency, will be given by. Now, F listener should be less than F source. Now, for this to be less than the frequency of the source, for the frequency of the listener to be less than the frequency of the source, we need to make sure that the numerator is less and the denominator is big, so that this fraction will be small, and then we'll be multiplying the frequency of the source with a smaller number. Then we will have a smaller value. So that means that the top part, which is our numerator, v, the velocity of the waves in the medium, we should, to make it small, the numerator, we should now subtract the velocity of the listener. And we divide this again by the velocity of the waves in that source, or the waves in that medium. This time, we want to make it big. It will be plus 0. Now, the plus, like I explained earlier on, says that we are actually increasing this velocity for us to have a smaller fraction. Okay? Then we multiply that by the Fs. Okay, so these two are the conditions where we have the observer moving towards the source and the observer moving away from the source. Now let's check and see what happens when we have the source moving towards the observer and the source moving away from the observer. Let's start with source moving towards the observer. Now, when the source is moving towards the observer, firstly, we know that what the observer is going to perceive as the frequency is going to be greater than the actual frequency of the source. And we also know, as given in the information here, that this time the velocity of the listener is 0. The listener is not moving. It is the source moving towards the listener. So, if we are to find the frequency as observed by the listener, because this is going to be big, we know that the numerator has to be big and the denominator has to be small. So v, which is the velocity of the waves in the medium, we will have to add the velocity of the source there, which will be the velocity of the source being 0 in this time. Sorry. It will be the velocity of the listener being 0 at this time divided by the velocity of the waves in the medium. This time we want to make this number big, so we are going to subtract the velocity of the source. And all this should be used to multiply the actual frequency of the source. Okay, so this is what will happen in this situation where the source is moving towards the observer. So all you need to know is that you need to tell yourself what condition am I working in here? Is it the source moving towards or moving away? Is it the listener moving towards or moving away? So we need to get that very clearly. Now, let's move on to the last bit here, where we have the source moving away from the observer. Now, when the source is moving away from the observer, FL is going to be less than the actual frequency of the source. Now we also know that VL is 0. It's not moving. What is moving is the source. Therefore, we want to make these FL to be less than the FS because the source is moving away. And in doing so, we are going to make sure that our fraction gets smaller. For us to do that, we should make the numerator less and the denominator big. So we're going to say that V here, for this one to be less, we're going to have the minus. But remember, the VL is 0. And then down here, we will have V, the velocity of the waves in the medium. We're going to make this big, so we'll say plus Vs, velocity of the source. And all these multiplies frequency of the source. Now, this is beautiful. If you understand all these conditions here, it's very clear. You can actually address any calculation based on Doppler effect if you understand this. I know that some of the problems are sort of made tricky and the examiners want to catch you, but they are not necessarily wanting to catch you. They're actually checking on how much you know and how critical you are when you're solving your problems. And we will see in some of the examples that I have for you today how you should approach some of these problems. And some of them, of course, a bit challenging, but very interesting, something that you love to work with as a science student. Now, let's now move on and start to look at some of the examples. Let's look at example 1. Now, example 1 talks about a fire engine. It has got a siren on, and it is moving and approaching a man standing by a roadside. The siren emits a sound with a frequency of 430 hertz. Now, we need to write this down. What is given to us? The fire engine has its siren on, and the siren is emitting sound with a frequency of 430 hertz. Now, this is therefore the frequency of the source, because this is the frequency of the siren, so it is the source. That S there is not necessarily for siren, but it's for the source, which is, in this case, happens to be the siren. Now, we are also told that the speed of the fire engine, as it is moving towards this man on the roadside, is 10 meters per second. So this will mean that the velocity of the source, which is the siren, is also 10 meters per second, because this siren is attached or built in on the truck, on the fire engine. So there is the information that we have. What other information do we have here? You should be critical about what is given to you as a question. Some of the information is not very clearly given to you, but you can actually deduce from the given question. Let's look at this. What is not given to us directly here is the velocity of the listener or the observer. But we are told that this observer, which is a man, is standing by the roadside. Now, if that man is standing by the roadside, it will mean that his velocity is 0 meters per second, because he is not moving. So for some people, that could be very difficult to deduce. But I am asking you to be critical with the question that is given to you. It's very clear here, but make sure every time to get the embedded information in what is given to you, which is not vividly or clearly given to you in terms of numbers and values. All right. Now, the question is, calculate the frequency of the sound heard by the man if the speed of sound in air is 340 meters per second. Now, this is now V without any subscript. This is the velocity of the sound waves in the medium which is air. So as the sound waves move in that air medium, we are told the velocity at that point is 340 meters per second. Now let's see how we can calculate for the observed frequency. We now have all the given information. Well, all we need to do is to put it into the required formula. But remember, we are not going to write down the general Doppler effect equation where we say FL equals V plus minus VL divided by V plus minus Vs times Fs. No, we're not going to do that because we know what we're talking about. Here, the fire engine is approaching the man. Now, what does that mean? It means that as the fire engine approaches the man, the frequency observed by the man will be greater than the frequency of the source. Okay, so that is the situation we're looking at here. For this to happen, our fraction has to be bigger. So we are going to make the numerator big and make the denominator small. Now let's do that. So the frequency of the listener would be equal to V, and for us to make this one big, it will be V plus VL divided, and to make this denominator small, we are going to say minus the Vs, and all this will be multiplied by Fs. Okay, now then we can begin to substitute into this equation. Now I also want to mention to you that substituting values into the formula is very critical for grade 12s. In fact, for any science students from grade 10 upwards, you must take that very seriously, because you get marks as you substitute accurately or appropriately into the given formula. So take a careful look at your formulas and substitute appropriately, because that is how you are given marks in the marking center there. We look at how you are substituting. Are you doing it properly? We give you marks for that. And even your writing down of formulas. Now follow me as I do this, and I'll be explaining this further as we move on. Now, from the given information, we know that V is 340 meters per second. So for V, we would write 340. So I'm substituting correctly for V there. Plus the velocity of the listener. The velocity of the listener is 0. Divided velocity of the waves in the medium, it's 340 meters per second. Minus the velocity of the source is 10 meters per second. So all these in brackets multiplied by Fs. Now, what is Fs? Now, this is 10 multiplied by Fs is given to us, it's 430 hertz. So from here, all we need to do is to make use of our calculator to solve this problem. But we can quickly sort of simplify the brackets section here. 340 minus 0, it's 340. Divided by 340 minus 10, it's 330. Okay? This will be multiplied by 430. And then we're going to get our answer. Now let's use a calculator quickly to find the solution to this problem. So we have 340 divided by 330 times 430. let's see what the answer is. So the observed frequency is going to be 443. So 443 hertz, 0.0, so we can ignore that. 443 hertz. This is what the man will perceive as the frequency of the siren, as the sound as emitted by the siren from the fire engine. So now, I think this gives you an idea of how we calculate for the observed frequency. Right, let's go to the next example. Example 2, it talks about an ambulance moving and with a siren on, and the frequency is 600 hertz. It's moving towards a group of onlookers. Calculate the frequency of the sound heard by the onlookers when the ambulance 1 approaches and when it moves away. And we're given different velocities in which it approaches the onlookers and it moves away from them. Now, for number 1, we can write what is happening here. What we know is that the frequency observed by the onlookers is going to be greater than the frequency of the source. What is given to us is that we have the frequency of the source as 600 hertz. We also have the velocity of the source, which is at 80 kilometers per hour. I think that is too far for me. Let me just write it down properly for you to see it. So the velocity of the source is 80 kilometers per hour. So this is what is given to us, but we also know that the onlookers are stationary, so VL will be 0. Now we are also going to take, this is the velocity of sound in air, let's take it to be 340 meters per second. Now, because we're having kilometers per hour there and meters per second here, then we have to do our conversions. Now, to convert from kilometers to kilometers per an hour to meters per second, let's do it quickly here. We know that if we have kilometers per hour is the same as saying kilometer divided by 1 hour. Now, this means if we are to move from kilometers to meters, we'll have to multiply this by 1,000. So we've got 80,000. I will be quick here. Divided by 1 hour in terms of seconds, it's 60 minutes times 60 is 3,600. So we can quickly get the answer there, which will be 800 divided by 36. So let's see what that velocity is. So we need a calculator to quickly get the conversion here. It's going to be 800 there divided by 36. And that will be 22.2 meters per second. So that will be the velocity, 80 kilometers per an hour. Now we also have to, we can quickly do the conversion here because we're going to use it as well. So for the next part of the question, it will be, as you have seen there, this is going to be 9,000 divided by, or 90,000 divided by 3,600. So you have got 900 divided by 36. So let's do that. 900 divided by 36. And we get that to be, this is V source, which is now 25 meters per second. So that's for the second part. Now let's go back to the first part. We know that the frequency of the observed by the listener is going to be greater than the frequency of the source. So FL equals V. This must be small, so it will be V minus VL divided by this must be big actually, sorry, so it will be V plus, and then the small one here is the numerator, which should be V minus the V of the source times Fs. Now let's substitute into this. We have V, which is 340, minus VL, they are stationary, V minus Vs, V is 340, minus Vs is, sorry, up here, although it is 0, I need to be clear with my signs here. It has to be plus there. The bottom one is 340 minus Vs. Now, what is Vs? We have just calculated it in meters per second. It's 22,2, right? And what does this work out to? This should be multiplied by Fs. Now, what is Fs? It's given to us as 600, frequency of the source. Now, what is this going to give us? Let's work it out quickly. We can use the calculator immediately. 340 plus 0, it will be 0, divided by 340. I need to put in a brackets there because I've got two numbers to subtract. 340 minus 22,2, close brackets, and all these should multiply 600, and that is given as my answer. So the frequency is 641.91 hertz. 641.91 hertz. Now, this answer is also realistic because we expect the frequency as observed by the listener to be greater than the frequency of the source. Frequency of the source is 600 and 641 is greater than 600. Right, now let's have a look at what happens when the ambulance is moving away from the listener. Now, we know from the Doppler effect equation that we would have this as the V minus the velocity of the listener divided by V plus velocity of source, okay, and all these times the frequency of the source. And this will be equal to, now we're taking V to be 340, so this will be 340 minus 0. We know the listener is not moving, and down here we would have 340 plus 25, that is the velocity of the source, okay, and all of these multiplied by frequency of the source. We are given the frequency of the source as being 600, and when we work this out, you would see here you've got you would be having 340 minus 0, which is 340, divided by 340 plus 25, which is 365, and then you multiply that by 600, and you get 558.9 hertz. Okay, so it's 558.90 hertz. Okay, so that's 0.90 hertz. That's the frequency as observed by the listener. Okay, now let's look at the next example, and that will be example 3, right? We're having a question here that says an ambulance with siren on moves towards Mpo, standing at a traffic light. Okay, now there is information given to us there around that word standing. We will write it down later on. If the frequency of the ambulance is, of the siren of the ambulance is 240 hertz, determine the frequency of the siren heard by Mpo if the ambulance is approaching at a speed of 20 meters per second. Now let's write down all that is given to us. Here, that word there tells us something about Mpo. it tells us that the velocity of the listener, it's 0. Mpo is standing, is stationary. But we are also told that the velocity of the source as the ambulance moves towards Mpo is 20 meters per second. We are also told that the frequency of the source is 240 hertz. Okay, so all this is given to us. Now, what we are also understanding from the given information is that the ambulance is approaching Mpo, and therefore the frequency that Mpo is going to hear should be greater than the actual frequency of the source. So that's what we are expecting in our answer. Our answer should actually give us frequency greater than 240 hertz. Right. We are also given the velocity of sound in air, and this time it's given to us as 344 meters per second. Right. Now we can solve this. The frequency observed by Mpo will be given by. Now, like we have already said, moving towards Mpo means this frequency is going to be greater than the actual frequency. So the numerator is going to be made big, the denominator is going to be made small. So the top part will be V plus the velocity of the listener, which will be 0 in this case. And down here, it will be V minus the velocity of the source. And all this must be multiplied by the frequency of the source. And this will be equal to. Now let's substitute correctly into the formula. V is 344 plus VL is 0 divided by V is 344 minus Vs is 20. So we put 20 there. All these multiplied by the frequency of the source, which is 240. Now we can quickly use our calculator again to sort out or find the solution to this. That will be 344 plus 0, it will remain 344, so we'll say divide by, in brackets, 344 minus 20, close brackets, and everything in here should be multiplying 240. And let's see what the answer is. And definitely the answer is greater than the actual frequency of the source at 254.81. 254.81 hertz. So that is the frequency as observed by Mpo. Now let's have a look at example 4. Example 4 says the sound of waves produced by a jet has a frequency of 1,300 hertz. So that's the frequency of the source. And if the speed of sound in air is taken to be 344 meters per second. Now, the questions are: calculate A, the frequency heard by a crowd of people standing on the ground when the jet is approaching at a velocity of 494 kilometers per hour. Now, for us to answer this question, we need to take into consideration the fact that we're not working in kilometers per hour, we're working in meters per second. That is our SI unit. So that's one of the things that we need to take into consideration. And now, when we have converted, then we'll be able to calculate and find the answer to A. Now, let's just have a look at how we can do that. So, say we have the solution for A at that point. We know that we are given the frequency of the source to be 1,300 hertz. And we are also given the velocity of sound, which is V in this case, as 344 meters per second. We are also given the velocity of the source, which is the jet in this case, to be 494 kilometers per hour. Now, like I said, this kilometers per hour has to be converted into meters per second for us to answer A. So the conversion here, if you remember well from the previous examples we did, we know now that to convert from kilometers per hour to meters per second, we can simply divide whatever is given to us in kilometers per hour by 3.6. So let me do that quickly. So the speed of the jet in meters per second will be 494 divided by 3.6. And that gives us 137.22 meters per second. So that is the unit there. Now, you can work it out using your calculator quickly, and that is the value that you're going to get. So we know now what the velocity of the jet is in meters per second. So we can calculate or find the solution to question number A. Now, question number A, frequency heard by the people standing on the ground will be given by the Doppler equation. Now we need to think again. Is the jet approaching the people, or is the jet moving away from the people? Now from the question, we hear that the jet is moving towards the people. Now if the jet is moving towards the people, it means that the resulting frequency that is going to be heard by the people is going to be larger than that of the source. So for us to have a larger frequency, it means that the top must become large, so we'll add, and the bottom will become small. So I have already put the 0 there to say that the velocity of the listeners is actually 0. You would remember that here, this is where you have your VL. Now, this should be multiplied by the frequency of the source. Let's now substitute everything into it. What is V? V is the velocity of sound in air, which is 344 meters per second. So we'll put that in 344 plus 0 because the people are not moving, divided by the velocity of sound in air, V, minus the velocity of the source, and we found the velocity of the source to be 137.22 meters per second. So it's 137.22. All these should be multiplied by the frequency of the source. What is the frequency of the source? It is given to us as 1,300 hertz. Now let's get a calculator to work out the solution to this quickly. There is our calculator. We have 344 divided by, we'll put this in brackets, 344 minus 137.22, close brackets, and all this must be multiplied by 1,300. And that is our answer. The answer is 2162.68. 2162.68 hertz. Now, this answer is actually reasonable for our question. It's saying that the frequency heard by the listeners, heard by the people standing on the ground, is actually bigger than the real frequency of the sound as produced by the jet. We can check that. Remember that the frequency of the sound produced by the jet is 1,300 hertz. But because the jet is approaching the people at some speed, the observed frequency by the listeners is 2,000 162.68 hertz. Now let's move on to number B. Number B says calculate the frequency heard by the people on the ground when the jet moves away at the same velocity. Now there's something important here. This time the jet is not coming towards the people, but it is moving away, and we are told that it is moving away. The velocity hasn't changed. It is moving away at the same velocity, meaning that it is moving away at that velocity, 137.22 meters per second. So we can quickly calculate what that velocity is going to be, or what that frequency is going to be. This is number B. We're going to use the same formula. So let me write it down. This time, the jet is moving away from the listeners. Now, if it is moving away from the listeners, we expect the observed frequency to be less than the actual frequency produced by the jet. So this means that this fraction here has to be smaller. For it to be small, the numerator has to be small, hence the minus. And the denominator has to be big, hence the plus here. All these must multiply the actual frequency. So now let's substitute into it. This V here is 344 minus velocity of listeners. We are told they are just stationary on the ground, so it's 0, divided by the velocity of sound in air, 344, plus the velocity of the source, which is that of the jet, at 137.22 meters per second. Now, all these multiplies the frequency of the source. What is the frequency of the source? It's 1,300 hertz. Then we can work this out. Now, I also need to explain here quickly that you would see that I'm taking my time substituting correctly into the formula all the given information. That is very important because when you write your exams, that is how you are marked at the end of the year. We look at how are you substituting into the equation or into the formula. Are you doing it correctly or incorrectly? So that gives you marks as well. So please make sure that you follow that appropriately. Now let's work out the solution. And again, like previously, we need our calculator. Now this time we've got 344 minus 0, which is 344, divided by, I will put this in brackets, 344 plus 137.22, close brackets. All these must multiply the frequency of the source, which is 1,300. Let's get the answer. The answer is 929.30. So it's 929.30 hertz. Now, is this answer not reasonable? It is definitely reasonable given the fact that now the jet is moving away from the people, and we expect the frequency observed by the people to be lesser than the frequency of the source. Now, definitely if we compare 929.3 hertz to 1,300 hertz, this is less than that one. And our answer is actually reasonable. It's a very good question that we worked on. Please make sure that you practice more on this. But I've got one sub-question again based on this. And this needs your thinking. And I would perhaps expect you to think a little bit before I give you the answer. Let's have a look at it. Question C. Now, question C says, what frequency would be heard by the people on the ground when the jet is directly above them? Now, that's a key statement, directly above them. Now, let's talk about this. When a source is approaching the listener, we know that the frequency is going to be greater, the frequency as observed by the listener. And we also know that when the source is moving away from the listener, the frequency observed by the listener is going to be less than that of the source. And our calculation has actually confirmed that. But then the question here says, what is happening when you have got your people standing on the ground, the jet approaches, frequency getting greater as observed by the listeners, but as the jet gets here, at that moment when the people on the ground and the jet are sort of at the same vertical, same position if you were to look at whether they are moving to the right or left, okay? What is going to happen? The jet is directly above the people. At that point, what would be the frequency observed by the people? Now, let's look at it. When the jet is approaching, the frequency observed by listeners is greater. When the jet goes away, the frequency observed by listeners is less. But this time, the jet is here, the people are here. This is the ground. Definitely, here are the sound waves produced by the jet to the people. Here we are not going to see any change in frequency because the jet is not moving downwards, but it's moving in that direction. Say it was coming from left to right, so that will be the direction of the jet. So it is not moving downwards, and therefore there is no change in the frequency of the waves that are moving downwards, carrying in actually for the sound that is actually heard by the listeners here. These are your listeners, the people, observers. So there will be no change this time in frequency. The frequency of as produced by the jet will be the same as the frequency observed by the listeners. So FL will be equal to Fs equals to 1,300 Hertz. Now, example 5, like I said, a good one. Let's read through it carefully. It's again about ambulances. An ambulance traveling down a road at constant speed emits sound waves from its siren. A lady standing on the side of the road with a detector which registers sound waves at a frequency of 445 Hertz as the ambulance approaches her. Now, after passing her at the same constant speed, we are not told what this speed is. Sound waves of frequency 380 Hertz are registered. So the frequency has reduced here. Assume that the speed of sound in air is 343, so we're going to use 343 meters per second for the speed of sound in this question. The first question asked here is, name the phenomenon that describes the change in the frequency observed by the lady. We know that that phenomenon is called Doppler effect. Now, that is what it is, Doppler effect. So you get your 2 marks by saying that. Now, for us to answer the next question that says calculate the speed at which the ambulance is moving, we need to write down all the given information. Let me use this side here to write down all the given information. We are told that the frequency of the source, or the frequency observed, let me just write it down here. The first frequency observed, I will call it FL, is 445 Hertz. This is what has been observed or detected by the woman or the lady. Now, this is when the ambulance was approaching. So when it was moving away, we have got another observed frequency. I will call it F prime, FL. That will be 380 Hertz. This has been recorded as 380 Hertz. Now, we are assuming, or we are using the speed of sound v in air to be 343. We're taking it to be 343 meters per second. Allow me to write it like that. Don't have enough space there. Question 5.2a, we calculating for the speed of the ambulance, okay? But then we've got two situations here. The first situation, we've got a situation where the source is moving towards, okay, towards the listener. Okay, and here, when it is moving towards the listener, we are told that the listener, so this is the frequency that the listener is observing. The frequency is 445 hertz. Okay? What we also know is the speed of sound in air, which we will call V. We'll call it V. That's the speed of sound in air. V is 343 meters per second. Okay, so that's what we have. And we also have a situation where the source is moving away. So here, let me just write source moving away. For the sake of space, I'll write it that way. So when it is moving away, we are told FL, the frequency that is observed by the listener in this case, it's 380 hertz. But what remains common, it's your V, which is 343 meters per second. Now I'm doing this too so that we can understand that at the end we need to come up with two equations here. In other words, we'll solve this using simultaneous equations. Now let's start with the first scenario. We know that when the source is moving towards, the frequency must be bigger, that is observed. So we will have FL equals, now from the Doppler effect equation, we know that the top part will say V plus minus the VL. Now in this case, because it should be bigger, we would say it should be plus, okay, plus VL divided by. This bottom part must be a smaller number, so we need to have a minus between V and the Vs. So we'll have V minus Vs. All these should multiply the frequency of the source, okay? And when we are here, then we can substitute what is given to us, okay? Now let me get some space here. What is FL? FL for the first situation here moving towards is 445. So for the frequency of the listener, we'll put 445 as given up there. Equals, what is V? Okay, V is 343 minus velocity of the listener. We know the listener is stationary, so that will be 0. You divide that by V is 343 minus the velocity of the source. That's what we're looking for. It's Vs. Okay? And then times the frequency of the source. And if you work this out quickly, what you will find out is that you would have this as 445 equals. If you work this out, this is going to be 445 equals 343 divided by 343 minus Vs times Fs. Now we can actually cross multiply here, making use of our mathematical understanding. Therefore, this becomes 445 times 343 minus Vs, okay, equals 343 Fs. That is 343 times Fs, okay? And if you work this out, you're going to have it as 445 times 343. What we have there will be 152,635 minus, of course, 445 times Vs will be 445. 345 Vs equals 343 Fs. And this becomes your first equation. Now let's go to the right-hand side here and check what we'll come up with. In the same way, we know from the Doppler effect equation that FL will be given by V plus minus, but this time the source is moving away. Moving away means that your numerator, your fraction here must become a small number. So for it to become a small number, you need to subtract at the top and you need to add at the bottom. Okay, I think by now you're getting what that is all about, times the frequency of the source. Now if we substitute to this, we are told that in the second situation where the source is moving away, FL is 380. So for FL, we will substitute it by 380 hertz equals V at the top, 343 minus VL, again, L is stationary, okay, all in brackets divided by, what is V again? 343 minus, plus, that is plus velocity of source times the frequency of the source. Now if we work out this quickly, okay, 380 equals, this is 343 minus 0 is 343 divided by 343 plus Vs, the top there will say times Fs. Okay, so if you cross multiply here, what you will end up with is 380 times 343 plus Vs equals 343 Fs. Right, so you work that out quickly, it will give you 380 times 343 gives you 130,000, okay, 130,340 plus 380 times Vs is, of course, 380 Vs, velocity of the source, equals 343 Fs. Now, this becomes your second equation. Now, at this point, now that you have your two equations, you can work them out simultaneously to get what Vs is. Okay, you will see both of them have got Vs. But one quick thing to see here is that you've got this situation here, that all these equals 343 Fs in both sides. So in other words, this would mean that this part here, the 152,635 minus 445 Vs should be equal to 130 on the other side, 340 plus 380 Vs. And why am I doing that? Because both of them are equal to 343 Fs. Okay, and from here we can then quickly work out what this is going to be. You take this one to the other side, you'll have 152,635 minus this, and the answer for that will be 22295 equals, okay, then this one goes to the other side, it is a minus, it should become a plus when it goes to the right hand side, so you've got 380 plus 445 Vs, and that gives you 825 Vs. Therefore, Vs is equal to 22295 divided by 825, and that should work out to 27,02. Remember, this is Vs, the velocity of the source, and we measure velocity in meters per second. So in this way, you have answered number A. 27,02 meters per second is the velocity. Okay, 5b says, now find the frequency at which the siren emits the sound waves. Okay, now at this point, it is quite easy to find it because previously we now know what Vs is. We now know the velocity of the source. It is 27.02 meters per second. So all we need to do is to substitute this value in one of our simultaneous equations that we had earlier on. Okay, so you can choose between the two. You can use 1, you can use 2. Okay, and in my case here, I chose 2. Let's just go to 2. Okay, from equation 2 here, you see that equation 2 says you have got 130. Okay, you've got 130, 340 plus 380 Vs, giving you 343 Fs. Okay, and then Vs is what we calculated earlier on, is the 27.02. So when we substitute there, we're going to have it as 130, 340 plus 380 times Vs, which is 27.02. This will be equal to 343 Fs. And you work this out, you would find that you've got 130, 340 plus 380 times that gives you 140, 607.6 equals 343 Fs. Therefore, Fs equals 140, 607.6 divided by 343, and the answer that you're going to get there is 409.93. And this is frequency. It is measured in hertz, and that gives you the solution for 5B. That you need to understand how to work it out. I hope you enjoyed that, and you can work that out on your own. And just lastly, Doppler it's actually applied in real life in measuring the blood flow. We use that to do that. We also see naturally that bats use Doppler effect to actually locate their prey, which is insects. We also see the police, the traffic police, using radars to actually catch you on speed on the road. So it's very useful. Doppler effect is a very useful phenomenon in physics. We also use Doppler effect to measure speed in sport. When playing tennis, they know exactly how fast the tennis ball is moving. When they're playing cricket, things like that, they can see how fast that cricket ball is moving. I hope you've enjoyed this, and please keep well and study well in your science. I hope this helped you a lot in understanding more about Doppler. My name is Tinyiko Kosa, and thank you for watching. We'll meet the next time. Bye-bye.